right now I want to zoom in on this problem. Now, we've solved a few that look like this. We're finding the standard form for a given ellipse, and a lot of you have had a pretty good time going through these first couple of steps. Here I've moved my constant term over to one side, and I've organized by my variables, and I've factored out that leading coefficient. But when it comes time to try to complete the square and to go to this next step where we get 4 times x minus something squared plus 9 times y plus something squared, there's a lot of confusion. Now, I don't blame you because completing the square is tricky. And usually we're taught this rule that you should divide that term by 2. And if you divide it by 2, then magically that number will be the one in the square. Well, it's not magic and it makes sense. I want to show you a way of thinking about it. So to do that, I want you to think about just multiplication. Now, if you have learned how to multiply like most of us have, and you're trying to figure out something like 22 times 13, you'll probably do something like this. You'll set it up like this, and then you'll do some sort of algorithm. And we'll get 6, and then 6 again, add in a 0, 2200, and we get 286. But why? Why do we get 286? Well, there's a different way of thinking about multiplication. And instead of using an algorithm, I want to think of it as finding the area of a rectangle. I want to think about this rectangle as having sides of 22 and 13. Now that area should be 286. But there's another way for us to break this down. Instead of thinking of this rectangle as being 22 by 13, I'm going to think of it as being 20 plus 2 and 10 plus 3. Now, if I find the areas of all of these sub-rectangles and I add them all together, it should be the same area, right? But I've broken it down into smaller, easier problems. Now I can see that this rectangle right here is a rectangle that is 10 by 20, or has an area of 200. The second one has an area of 3 by 20, which is 60. There we go. 10 by 2 for an area of 20, and then finally 3 by 2 for an area of 6. And adding those all together, we get an area of 286. Word? Now, what's great about this model is that it works with multiplying binomials. So yes, I could use FOIL or to making every pair to find this to find what this expands to. I could do x times 2x, x times negative 3, 2 times 2x, and 2 times negative 3. But I can also think of this as x plus 2 multiplying 2x minus 3. And this gives me one rectangle with an area of 2x squared, one with an area of 4x. To get that, I did 2 times 2x, those two sides of my rectangle. One with an area of negative 3x, and one with an area of negative 6. And combining these two like terms, I'll end up with an area of 2x squared plus x minus 6. Now, let's just check that. If I do x times there, that's the 2x squared. 2 times the 2x gives me the 4x. X times negative 3 gives me the negative 3x. And then 2 times the negative 3 gives me the negative 6. It's the same thing. I'm just representing it visually. Now, here's why I'm bringing this up. Let's think about something like x minus 3 squared. If I'm using this same strategy, I'll draw a rectangle and find its area. I'll have x minus 3 times x minus 3. And I'll have one that's x squared, one that's negative 3x, one that's negative 3x, one that's positive 9. And these terms combine, and they combine equally. I have negative 3x and negative 3x. There's symmetry here. And I end up with x squared minus 6x plus 9. But now you can see why people divide this term into two, because the two pieces, these two rectangles, are always equal. So let's think about it in context now. Let's say you're trying to complete the square, and you add x squared minus 14x plus something, and you're trying to figure out that something to complete the square. Well, in this case, our rectangle would look something like this. X minus something times x minus something would give us x squared here, and 14x split into these two pieces. Well, that 14x splits equally into minus 7x and minus 7x, which means that the top two bits must be minus 7, so our total down in the bottom corner is 49. Now I hope this feels like it's making way more sense, because now we can see that we're adding 49 to complete that square, which means inside the perfect square binomial, we have x minus 7. And we can transfer that up to here. Now we can see why this ended up being 5. But just so we can visualize it, for this y term right here, if we're trying to figure out what is going to add up to 10y equally, y plus something, if we have y squared, and we have 10y in two pieces, that means we must have 5y and 5y, which means it's y plus 5 squared, or 25 being added initially. The same thing is true with our x term as well. We can see that we have x squared minus 12x. So if we have x minus something, we'll have x squared and minus 12x split into two pieces is minus 6x and minus 6x. So that other length on a rectangle must be 6, which gives us 36. 36 as our term up top, and x minus 6 squared in the bottom term.